Hey there and welcome to this video in which I'll be going over the workflow for the automated analysis of Derenzo micropet phantoms in Immulytics Preclinical. Derenzo phantoms are used for the assessment of image quality and resolution in PET and SPECT scans, and Immulytics Preclinical provides an automated workflow to obtain all the relevant quantitation in just a few simple clicks. So we can start by loading up our tutorial dataset, which we can find just over here. We also provide a white paper which states all the methodologies used in obtaining the quantitation. Once we load this up, we can see that we have a PET image overlaid on top of a CT image. We can turn on interpolation to get a smoothed out visual of it. And the first step in the analysis is performing a Hounsfield unit calibration of the CT image. So the CT image is used to obtain the localization of the phantom in 3D space, and then we can draw the appropriate line profiles on the PET image, which should be perfectly co-registered to the CT. So this CT is already calibrated to Hounsfield units, but I'm going to demonstrate the workflow. So what we want to do is first create a channel or a class called a water. I like to turn off the overlay for this as it makes the segmentation a little bit easier. So the Derenzo phantoms have this linearly filled channel that runs throughout the entire phantom. And in this we have our solution, which is a water-based solvent. So what we can do is segment these voxels, as we know this is water, and so that the intensity of these voxels should be at the literature value for water in Hounsfield units. So we'll segment a few different regions of water from the phantom, just a few different areas. And then what we'll do is create an air channel and do the same thing. I like to use these screw holes here because it's within the phantom, so if there's any depth effects that are taking place, they're accounted for. We can also do some regions on the outside as well, just like that. So what we want to do is now ensure that our underlay is selected, our CT, and go to Math, Hounsfield Unit Calibration. Now once that's done, we can go ahead and delete all of our classes. The next step is to obtain the model number of the Derenzo phantom. So we can see that in the 3D view if we adjust our window a little bit to be able to see the body. So what we can see is that at the surface of the phantom here, we have the model number. So this says D271020. So we just want to make note of this, as the next step will ask us for the model number. So we go to Nuclear, Phantoms, Phantech Phantom, and select our D271020. Now once the algorithm is complete, it'll give us this table with all of the quantitation necessary. So what we get here is a table with the average percent recoveries for each rod diameter. So these diameters are respective to the model number, and so if you select a different model number, you'll have different diameters. And we also get the full width half max, which I'll explain the computation of in just a moment. So these average percent recoveries are then plotted with respect to diameter over here. And what we do is we fit a sigmoid curve to this. The inflection point of this sigmoid curve, which is where the fractional recovery is at 0.5 or 50%, is then reported as the full width half max. So as we can see here, it's about 1.58, and we can see here 1.58 as well. Each individual line profile is also plotted over here with a little legend showing the different diameters. So to obtain these average percent recoveries, what we do is, I'm just going to turn off the phantom segmentation here and the underlay so we can see exactly what's going on. So we have all these segmentations, and these segmentations are color-coded based on diameter. So the pink is the 2 millimeter here in this case for this model of phantom, and for instance the blue over here would be the 1.6 millimeter, and so on. And in the overlay we have these markers that get placed. These markers are placed 3 per rod, so it is technically one linearly filled channel, but certain regions of it are constricted to certain diameters. And so what we have is a marker placed at the geometric center of each rod at 3 planes orthogonal to the length of the phantom. So for each plane, this would be the first plane, then the second plane, then the third plane, we perform line profiles for each section. So if we go to one of these and find the markers, we can see So for instance here, in this 2 millimeter, I'll turn on the underlay so it's a little bit easier to see as well. Let me just adjust the window here. So for each grouping in one plane, what we do is we take the geometric center of the rod and trace a line profile from that geometric center to all the adjacent neighbors in the same grouping. So for this grouping of 2 millimeters, what we would do is a line profile from here to here, here to here, and here to here. So that comes up with 3. We repeat this for the 3 planes, right? So that's the second plane, and then there's a third plane further. The averaged percent recovery is the averaged percent recovery for each line profile per group of all planes. So what that means is if we have 3 line profiles in this plane, and then 3 line profiles in the next plane, and then 3 line profiles in the next plane, that's a total of 9 line profiles from which the average percent recovery is then reported as the percent recovery for this grouping. So the percent recovery is computed as the average value at each geometric center. This would be referred to as the max, and then the midpoint. So we take the average max value, subtract the midpoint, and then divide that by the max, and that's the percent recovery. You can consult the white paper for more information on the quantitation methodology, or send us an email if you have questions. Now, what I want to demonstrate in the end of this tutorial is sometimes the image quality of the CT is not sufficient to perform the localization of the phantom in 3D space. So to illustrate this, I'm going to downsample the CT, so we can see right now that it's at a resolution of, that's for the PET, but for the CT we have a resolution of 0.2 millimeters, 200 microns. What we can do is downsample this by 2, and what we see is now we have a resolution of 400 microns. Now, if your image quality looks like this, you'll often run the function, just as you would, and it would take a little bit longer, and you would get an error message at the end. And so we'll let that pop up over here. And so that can sometimes take a couple minutes, but once we get our message, we see that it says, unable to perform auto segmentation. Please create a class called mask and fill the class with small spheres located at the cone tips. Once completed, rerun the function. So what we want to do is find the cone tips on the phantom. These are used for the localization in the CT data. We can turn off interpolation to see them in a more contrast. And what we can do is create a new class called mask. Then we go to our create region tool, select a sphere. I like a diameter of 2, but it's sort of irrelevant. We can go to our cone tips and then create a little sphere. So we're transferring voxels from unclassified to mask at the cone tips. It doesn't really matter if the center of the sphere is at the cone tips, as it's using the entire sphere for the localization. But once this is done, what we can do is go back to our menu, click Phantech Phantom, select our Phantech model, and it should run quicker this time and hopefully give us better results. So it says here a poor alignment has been found, and this can sometimes be because the resolution makes things less spherical, but we can see what that looks like over here. So we can see that our full width half max is actually quite similar as it was at the higher resolution, and we get all the same statistics. We can also evaluate the registration here by scrolling through. And we can see that it actually looks pretty good, all things considered. If you have any questions about this, please feel free to reach out. But that's it for today. Hope you enjoyed the video. Take care.